Hello everyone, my name is Duan. In this video, I'm going to present my course project for 690, and I entitled it as Classify liana-infested canopies using UAV-based remote sensing techniques. So you can see this project is in the field of forestry and remote sensing. Okay, let's start. First of all, I would like to introduce what lianas are. So lianas are structural parasites. They can move from the host tree to others. They compete above and below ground resources with host trees. Lianas also reduce trees growth and increase trees mortality. But most importantly, liana infestations will reduce forest-wide carbon uptake. Tropical forests are a major carbon sink, but they usually suffer liana infestations. Selective liana cutting is a highly cost-effective natural climate solution. So scientific classifying and the mapping of liana-infested trees contribute to forest regulation and the decision-making of liana cutting. That's the main goal of this project. This project was carried out in a specific liana-infested forest patch of Santa Rosa National Park, Costa Rica. I used different remote sensing data sites according to corresponding objectives. And this flowchart summarizes the basic and the key steps in this project. Based on a high-resolution RGB photo, I classified lianas, healthy canopies, and forest gaps. It's like a visual interpretation process. For that thermal infrared image, I derived temperature. And for the multispectral image with 4 bands, I derived those 4 bands plus 1 vegetation index. That's NDVI. It's calculated by red and near infrared. Besides, I used LiDAR data to derive tree height information. So finally, I used all these metrics or variables to develop a random forest classification model. Based on that high-resolution RGB photo, when we zoom in it like this, it's very easy to distinguish lianas, healthy canopies, and forest gaps. So I classified the entire plot and divided it into 2 parts. The red part was used as training data sets to develop the model, and the left part was used as testing data sets to validate the model. Here are some raster images derived from those remote sensing data sites. That's a canopy model that shows height information, a multispectral image that has 4 bands, a thermal image that shows temperature information, and finally, NDVI map that shows NDVI information. I just put all this information into the final data table, and it looks like this. Furthermore, I plot the frequency density map for temperature, NDVI, and the tree height. Here are the findings. So for temperature, liana-infested canopies are warmer than healthy canopies. For NDVI, liana-infested canopies have lower NDVI than healthy canopies. For tree height, liana-infested canopies are shorter than healthy canopies. So all these 3 variables have potentials to be reliable predictor variables to develop the model. For the developed model, 1,000 random forest trees were built based on manual iterative examination, and other relevant parameters can be seen in the screenshot. The accuracy of the developed model was evaluated by a confusion matrix. Furthermore, to improve the computational efficiency and remove redundant information, I explored the importance of all predictor variables and determined the optimum variables for the classification model. The results show that temperature, height, and NDVI are the most important 3 variables as expected. However, for bands, especially blue indicate relatively weak contribution to the accuracy of the model. That's all about it. Thanks for your attention.